various versions of this. One of the problems is on how do you come up with the weights for the hidden layer. It's pretty easy to adjust the output weights going into the output, but the weights for the input, and they use what they call as a back propagation algorithm. And to be frank with you, I don't understand it, never tried to. But basically that's one that requires that you have a smooth output versus input, so they can differentiate it and somehow come up with an answer. One of the things that I think, I guess I first ran into the neural networks probably in some robot books. I don't know how many of y'all run them, you know, like Robot Bonanza. I think there may be a chapter or something. Most robot books have a small chapter on neural networks. And I think that the attraction is that they have the capability of learning. One thing that got me kind of interested in them was one day I was sitting there and realized something, and I'd like you to take your finger and touch your earlobe with it, like that. Now think about building your android that has the capability of doing that. I don't know, you know, your little arm has got a forward kinematics, where basically it says forward kinematics is about if you know what the angles are, where is the actuator. Reverse kinematics is you know where you want the actuator to be. Now what are the angles of the joints? And for simple mechanics like that little arm that Ron and I built that reached out there and grabbed the puck and slid it off to the side, those kinematics are rather simple because it only involved two joints and two fixed lengths. But you think about this, you know, there's a finger and a joint here and a joint here, you know. It makes me wonder whether I could come up with kinematics, and so I wondered, how does the body do it? You know, I don't think the body knows how to do trig. At least I don't think it does. And so, obviously, you know, so the question in my mind was, is it possible for a neural network to do inverse kinematics? And I think the answer is yes. I think it's possible. I don't know whether you can learn it or not. I guess there's another point. You got to understand, I didn't practice this speech very well. Hope you'll forgive me. One of the problems or concerns in neural networks is how do you represent things on the neural network? What they call is local representation, where each input, one input represents one something. And then they've got what they call distributed representations, where any one value or any one feature is distributed as a bunch of values. And so say you got a dozen inputs, all of them have some value to them for each input that you might have. I know this is kind of general, but let's say that, you know, if you were wanting to build something that had an inverse kinematics, you know, the inputs obviously might be X, Y, and Z of where you wanted the actuator, and the outputs then would be values for each one of the angles. And the question is, does each neural unit, does it have an analog output, or is it just a 0 or 1? And if it's an analog output, then obviously that output of that 1 could be the angle that you're wanting to move, but you're limited in accuracy with an analog simple analog output. So it may be that it actually is a distributed output. It involves several, and likewise the input. And it can vary all the way from a digital input, or it could be where each input was I'm going to say a bump. In other words, this output of this input unit would be maximum at, say, 5 volts input, or 5, say, a position of 5. And it would give an output at 6 and 7, but less output, so that if you looked at any one of the input units, how much it would be given to the next unit would depend on what the input was, but it would be a hump, and then they would be humped like this. I think your color vision is somewhat that way, in that I think you've got 3 different kinds of cells in your eye that look at different frequencies of light, but they're not sharply tuned to one that would just respond to green light or blue light or yellow light, but they have a broad tuning, and so you get one hump here. If a light frequency is somewhere in between the two, you can tell it by how the ratio between the ones, and that would be, I think, a form of distributed input. Like I say, my interest was primarily is can you compute with it, and what kind of computations do neural networks do? And it obviously can add, because the inputs are sums. The question is, can you do multiplication? And the answer that I seem to come up on with that is that you can create a function of the input, of a single input. In other words, like you can get an output, the square of the input, or that it's a sine of the input, or it's the logarithm of the input. Well, if you can get the logarithm, then you can do your multiplication by, first thing you do is take and convert it into the logarithms and add them. But there's that, you can also multiply by another technique. It turns out, and without a chalkboard it's going to be hard to say, but there's other functions that you can allow you to multiply. For example, there's one where and I don't remember it offhand completely, but if you take the square of one of the factors, and if you take the square of the sum and the square of the difference and subtract them and divide by 2, that's the product. It's something I can, if anybody's really interested, I can get a pencil and paper and show it to you. But so there's I guess the point is there's really not you're not stuck with logarithms. You can, anytime you create some functions and add them. So I think the answer is there's no question that a neural network can actually compute. And
so you're talking about a biological neural network, right? I mean, because there's no reason that you can't create something that'll multiply, a neural network that'll perform multiplication.
Well,
but not in the strict sense, I guess.
Well, if you